The first lecture dealt with the lattice energy of ionic solids, and we constructed Born-Haber cycles, and that's all important. But the second part, I'd like to focus on the structure of some very basic ionic solids. So this is an X-ray diffractometer, and I'm going to insert some stuff from my Gen Chem now, so it'll be really weird, but it's going to save me some time, and I really am kind of in a crunch, so forgive me for that. Basically, the way that atoms are arranged in the crystalline phase, right? Because you can have solids that are in a powder or just an amorphous surface. It doesn't have to be a crystal. But if it is a crystal, we can actually use X-ray analysis to determine all of the content of that crystal, all of the atoms that are in it, and the distance to each other, and then the bond angles. And so this is a very important technique that we use to determine the structure of materials and molecules. As long as we can grow a crystal or find a crystal, we can do that. And so what happens is the atoms in a crystal will arrange over three-dimensional space just the same way. Okay, so you get trillions and trillions of atoms in a particular crystal, and if they are always at the same distance and the same repeating unit, we call that a unit cell, then we can use that X-ray analysis. Now, these crystals shown here are all of the same material. It's called alum. You may have heard of it. Alum is used for pickling to keep the cucumbers crisp, I guess. So this is called alum. And it's actually an ionic solid. It's potassium aluminum sulfate. Okay, so you've got potassium, aluminum, and sulfate ions. This is an ionic compound, and when you dissolve that and you let it slowly evaporate, then you can grow these crystals. So as I said, these are all the same. You can kind of see they kind of grow triangular, and but that's not important. The importance here is that if there are no cracks, and if you have a single crystal, and it doesn't have to be a very large one, you can use this X-ray analysis to determine the content, right? For example, here we have, this is sodium chloride. We call this a unit cell. In green here we have the chloride atoms, and in red we have the sodium ions. Okay, so chloride ions and sodium ions. And so if you take a crystal out of a salt shaker and you do an X-ray analysis on it, you'll find that this is how these solids order, right? And so we know this already because we talked about ions, right? We have cations and anions, and I already told you that those spheres will connect and electrostatically, and they're just kind of packed like this. Now here it's shown where you can actually see a little bit more detail the atoms, but of course these atoms in real size, we'll see pictures in a minute, they're much larger, and they touch each other. They pack as tightly as possible. So sodium chloride is a cubic unit cell. You can see it looks kind of like a cube, and so you have the length, height, and width all of the same. So we have here A equals B equals C. They are all the same, and so this is equal to the length, and that makes that a cube. And also all of the degrees are 90 degrees here, right? The angles, not the degrees. The angles are all 90 here, right? And so then if you take a look at the center here where the chlorine is, you'll see that they are actually 6 of those sodium ions. It's kind of hard to tell, but there's actually 6 sodium ions that are attached to that chloride. So that has we call that a coordination number. Oops, that's an N coordination number, and the coordination number for chloride here is 6, meaning it is surrounded at the same distance to 6 other ions. And it's also important to note that this is the smallest repeating unit, right? So we have this cube here with the content that's shown, and so if you put another cube next to it, we'll see if my art survives this. Too bad. It will have the exact same content, right? And so then there's also some parts where where the atoms are shared, right? So like this here, the sodium on the corner here, is actually sharing not just 2 other cells, right? Because it's actually 8 different cells, because you have to, and this is where my art is truly going to fail. But so in order to completely enclose that, you have to put, and then you have to put a second layer on top. I'll try my best. You kind of get the idea. Oh, it's turning out not to be too bad here, right? So in order, and then there's yeah. So there are actually 8 cubes. What this means, to make a long story short, is that this particular atom on the corner there is part of 8 total cells, which means it only contributes 1/8 to the unit cell content. All right, and we'll look at that in more detail. Now, this is a cartoon showing how X-ray crystallography works. All right, so the instrument used is called an X-ray diffractometer. You basically are shooting a focused beam through a slit here. That's how you can focus it into that single crystal, and the X-rays will bounce off the atoms at a certain angle and create a pattern here, as you can see on this plate, on this detector. And you have to collect about 7,000 or more beams, depending on how complex the structure of the molecule is, and then you can determine the bond distance here, right? This is a hexagonal cell that they're showing here. You can then determine the distance between these atoms and all of those bond angles and how they arrange over 3-dimensional space. And then the smallest unit of the repeating crystal structure is called the unit cell, which I've already said like 3 times now. This is what an actual diffractometer looks like, and it allows you to twist the crystal and collect from all angles. There's a device called the guyometer that can rotate. Your crystal is actually mounted inside of a very tiny glass capillary, so it doesn't shift. So this thing rotates, and the X-ray beam is shot through here. It is stationary, and so the crystal rotates, and so you can also rotate this disc so you can get collecting data from all different angles. Now, it turns out that there are 7 major crystal systems in which all molecules crystallize or are found in the crystalline state in nature, or when they had to crystallize at some point. And they are not all cubic. They get more and more complex as the length, the size differ of the box, and all the way to even a hexagonal cell. And so you have to remember that this is just a single unit, and that then all of these boxes or shapes are connected to fill out over 3-dimensional space. And here's just a summary. You can see for the most ordered one, the cubic unit cell, where all the angles are 90 degrees and all of the length of the edge are the same. And then you just change one of these length, and so you now have a box, not a cube. Keep the angles the same. It's a little bit less symmetrical, and that's called a tetragonal unit cell. And you just make it less and less symmetrical, and you end up with a triclinic cell at the end, which has none of the degrees are 90, everything is different, or even a hexagonal cell, as I mentioned. So this is a molecule. It's cyclotrimethylene trinitramine, which is an explosive. It's referred to as RDX, much easier, rolling over the tongue, RDX research. Explosive. Anyway, that's not the point. The point is that if you have a more complex molecule, it can't pack as tightly as individual atoms, but they still crystallize in a unit cell. And this looks like a tetragonal unit cell to me. It's hard to tell, but looking straight at it, it still looks like a square. But then one of the length is different here. The one that goes to the back, whether that's the width or the length, who knows, right? It depends on how you're holding that crystal or the unit cell. So this is the repeating unit, and so you see parts of molecules sticking out, right? If we look at this part that sticks out on top, it is actually part of the next unit. So we expect that to find that down here, and we do. So that exact part that's sticking out is of course on the other unit cell that's connected on top, to be found again. And you can do this with every single part of this unit cell here. Like here's a part that's sticking out to the right of it, and then obviously you're going to find it here. It dissects the molecule, but the repeating unit is here nicely shown, and that's why I selected this particular slide, because it shows nicely what the repeating unit is here. This is an example of an ORTEP diagram, Oak Ridge thermal ellipsoid projection. So Oak Ridge Laboratories was one of the labs for the Manhattan Project, right? And so go figure, they played around with X-rays, but we got some useful stuff out of there, as I told you already. But so this is an inorganic compound, square planar, you can kind of tell. But the point I want to make here is, first of all, usually we don't really show the hydrogens. You can have them drawn in. Hydrogens don't have a lot of electron density, so you're not going to be able to detect them necessarily. They're really tricky to detect. It's just one electron, so the larger, heavier atoms are much larger to detect. So those are usually calculated, but we can detect the bond distances and bond angles of everything else. And so this is a really nice diagram, and you can tell because all of those spheres, these ellipsoids here, are very spherical and small, and so some of them are a little bit wacko here, right? So this is molecular motion that you're seeing, right? The more this moves, the more stretched this is, or the larger they are, the more molecular motion you have. And so we also try to collect this data at very low temperatures, but it's pretty simple. And then you can measure all these look like perfectly square planar here, 90 degrees. And I just wanted you to see a couple of examples of, here's a copper complex here. Everything in black here you have labeled are the carbon atoms, and so it's kind of nice. You can color code. I should actually, I'm going to do this. I'm going to show you my structure. I should actually be not that modest. My structure, like I only have one. I have like 30 of them. Anyway, I've got tons of publications, and since I'm an inorganic chemist, it's going to involve growing crystals. But the reason I'm really proud of this one is because this was undergraduate research. One of my research students made this compound. He designed this ligand here. It's a diazacylophosphatidine, and then we were lucky enough to be able to get a free crystal structure by Brooker. I don't have a great connection, but they were happy to run this for me and send it to me for free. This is also a nickel D8 square planar complex. We knew it would be square planar because it was orange, but anyway, so you can see here the thermal ellipsoids and the hydrogens are projected, as I told you before. Anyway, I don't want to talk about this much with you. As I said, we will look at only a few of the cubic unit cells. Here are 3 examples how atoms can pack differently within the cubic unit cell. The simple cubic unit cell shown here on the top only has atoms on each corner, which we would like to determine the unit cell content, and so we already know that each corner is 1/8 of the contribution. So if you have 8 corners occupied, there's only a single atom occupying the unit cell. So there's just one atom in here inside of it, and you can also see that the packing efficiency is not very good here. You have a lot of empty space, right? And so the packing efficiency, which is something we're going to be looking at, is only 52% in a simple cubic cell, unit cell. We also want to be able to look at the radius and length relationship. So we're going to be looking, you can kind of see that in the simple unit cell. It's easy to see that because these 2 atoms are connected without any space, whereas here there's some space, that the length is going to be equal to 2 times the radius, for example. That's easy to see. So, but we want to be able to do that for the body-centered cubic unit cell as well as the face-centered cell. So we're going to look at packing efficiency. We're going to look at the relationship between the radius and the length of the unit cell, and the coordination number, so how many other atoms are attached to each other, and then the cell content. So that's what we're going to be looking at. So for now, the body-centered unit cells, of course, packed a little bit more efficiently. You insert an atom into the center, and so that goes up to 68%. You can really nicely see, if you look at this picture, that we have an entire atom. You can nicely see that the entire atom is completely embedded in the unit cell inside of it, and whereas the one in the corner is just a 1/8. So this chunk is just 1/8 of one of the atoms, which is part of the cell, and so it's really nicely shown in the space. It's really hard to see on top, but it shows us where the atoms are located, and as long as we understand inside means the entire atom is part of the content, and on the corner just means it is a 1/8, and then for the face-centered cubic unit cell, if we have an atom on the face, you can see this is cut in half. So each atom on the face is contributing a half to the unit cell, which means for the face-centered cubic unit cell, if each face has the 6 sides, has one, that means there are 3 atoms total part of the unit cell. Of course, here you also have the corners. We'll look at each of these in particular. For now, I just want to say the face-centered cubic unit cell is the one that is packed the most efficiently at 74%. And so next we're going to look at those things that I said. You know, don't even go get a Coke. Just go watch the next video. Okay, so we're looking at cubic unit cells. We saw 3 examples, and part 1 goes through those 3 and looks at coordination number, which is how many other atoms are connected to each other, and how many atoms are in one unit cell. So we expect that cell content to be the lowest for the simple cubic unit cell because its packing efficiency is lowest, right? And so all we have here are 8 atoms on each corner, which each atom contributes 1/8. So 8 times 1/8 equals 1. So the unit cell content is 1 atom per unit cell. And it's a little more difficult to see how many atoms are connected to each other here. And if we're looking at this atom here, we can see there's one to the right, one above, and one in the back. But you have to remember that we have also cells connected to each other. So looking at that particular atom, we have actually 6. So the coordination number is 6, right? So there's another one here, and then there's another one here, and another one here. So that's what we're looking at for coordination number. Simple cubic unit cell coordination number 6, and the atom content is 1. Moving on to the body-centered cubic unit cell. So now we have a higher packing efficiency. We are expecting to have more atoms in the cell, and we do. We have 2 because we still have the 8 on the corner, which contributes 1, and then we are adding the one that's in the center, completely embedded, completely 100% part of that cell, which you can tell the golden sphere in the center is completely embedded. And so this the coordination number is actually easier to see here than it is here, because you can tell that the one in the center is connected to all 8 atoms on the corner. So coordination number 8, and unit cell content is 2, the one in the center, plus the 1 for the 8 corners. Looking at the face-centered cubic unit cell, you can of course look at the answer. It goes up. Your packing efficiency is the highest there, so we expect that. We have, instead of an atom in the center, we now have 6 atoms on the face, and each atom on a face, we have 6 faces here, contributes a half. That's a total of 3, and then the ones on the corner is 1, and so we have a total cell content of 4 atoms here. All right, and the coordination number, of course, is 12, and it's a little bit more difficult to see where the 12 are, but I'm having a little bit of a hard time myself, so let's just stick with 12. Right? We'd have to rotate. I'd have to look at a physical 3D model. All right, so let's take a look at, we can do this without guidance now. We can look at a random unit cell. This is cesium chloride, and determine the content. Of course, now we have two different atoms. We have cesium and chloride atoms, whereas the ones we looked at all had the same type of atom. They're either aluminum or platinum, or usually a single metal that will pack efficiently like that. So this is pretty easy. It's a body-centered unit cell, and the one in the center is of course a cesium, and then we have 8 on the corner, and so 8 times 1/8 is also 1. So these are in a 1-to-1 ratio. There's one cesium atom or ion and one chloride ion per unit cell, and it makes sense that they are in a 1-to-1 ratio because we know that cesium chloride has the formula of CsCl. All right, jumping to something drastically more complicated. Okay, this is a cubic unit cell, but it is sodium chloride, which is in a 1-to-1 ratio. And so the new thing here is we have atoms on the corner, right? We know that we have sodium ions, not the corner but the edge. The chloride ions are on the edge. So this is something new that we haven't seen. But we know we have sodium ions on the 8 corners. So we have 8 times 1/8, which is 1 sodium ion on the corner. And then we also have sodium ions on each face. So all 6 faces have a sodium ion. So 6 times 1/2, which is 3 sodium ions. And so we have a total of 4 sodium ions in the unit cell. And then the chlorides, we have 1 in the center. All right. So there's 1 chloride in the center. And then we have the edge. Okay, so these are here all on the edge. And so if you look at this as layers, right? So we have 1 layer here, and the second layer here, and a third layer there. Each layer has 4 of those, right? So 1, 2, 3, 4, and then 8, and then 12. So there are actually 12 on the edge. So 12 atoms on the edge. And so you have to imagine the percent that this is part of, and it's actually 1/4, which then gives you 3 chloride atoms. You add them up, you have 4 chloride atoms. The total unit cell content is 4 chlorides and 4 sodium atoms or ions. And just in case you don't see it, right, that this is 1/4, just imagine how many cubes it would take to completely embed that, right? So if you have to have 4 cubes that are connected to get the corner completely embedded. All right, so moving on to the next factor. So we want to know packing efficiency. We've done the coordination number, and we have done cell content. Now we're going to look at the relationship between length and radius of a unit cell. The simple cubic unit cell is actually pretty easy to determine, right? Because they touch each other here. So we have 1 length is going to be equal to 2r. So there's no gaps like there are along the length, and all of the length here, of course, are the same. So that's basically it. So the cell length is equal to 2r. Gets a little bit more complicated for the body-centered unit cell. You've got a little bit of a gap here, so L is not easily expressed in terms of R. We have to use a little bit of math here. And so if we look at a section of this cube that is completely connected by atoms, it would be the diagonal through the entire group, from not on one of the faces, but from one of the opposite corners here, right? So we can see that there's half of a purple one, a full, and again, it's just color coding, so you can tell them apart, but they're all the same atom. They have the same radius. Otherwise, this math does not compute. So here, the distance C is actually equal to 4r. Okay, and so we use Pythagorean theorem, where we can argue that C squared, because you have a 90 degree. It doesn't look it, but it's a 90 degree angle here. So we can say that C squared equals B squared plus L squared, and if we want to express L in terms of R, you want to get rid of C and B, we can start doing that by saying, okay, so 4R squared equals B squared plus L squared. Now we need to find a relationship between L and B, and that one is very easy here because we have another triangle here with a 90-degree angle. So this is L and this is L. So we also know that B squared equals L squared plus L squared, and if we substitute that, we get 4R squared plus L squared for this, plus L squared, which is equal to 3L squared. If we put everything, if we isolate L now, so I'm going to divide by 3 on both sides. I'm going to put L on the left, so I'm going to say L is going to equal to, I still have L squared, 4R squared divided by 3, and now if I take the square root of both sides to get to have L by itself, I then get L equal to 4R divided by the square root of 3. And so this is the relationship of L to the radius. I prefer to move straight to determining the unit cell content. Now we already did this one. We know that atoms that are on the face here, so the face shares one other cell, so the cell content would be 1/2. Something on the corner would be 1/8, and then something on the edge would be, and I have this on the next slide, so I might as well, on the edge would be 1/4. And so this is regardless of, and I forgot of course the center, but anything that's completely embedded in the unit cell. And so we're also going to look at cells that are not cubic or well ordered, so you need to kind of pay attention and determine this. So let's just go through some simple ones here. This is a cubic unit cell, and in order to calculate the content, all you have to do is say, okay, we have chlorides on the corner, all 8 corners, so 8 times 1/8 chlorine on the corner, which is equal to 1. So there's 1 chloride ion in the unit cell, and then we have 1 cesium ion, and we expect that, right? Cesium chloride has, it should, at least the smallest ratio should be 1:1. That might be like sodium chloride 4 and 4 in there, but at the end of the day it's a 1:1 ratio, so we can kind of expect that. On an exam or a quiz, I may not give you the charges, so you'll still have to do a good job showing this. And this kind of nicely shows here the ball, the cesium in the center is completely embedded. It's a sphere. It's the whole single atom is part of the unit cell, whereas this is just 1/8 here. The chloride's just 1/8, so you need 8 other cells to completely embed it. And that's why we have this. So this is just 1 chloride and 1 cesium. That's the unit cell content. This zinc sulfide here gets a little bit more complicated, and I suggest that you start with ions that you recognize, that you know for certain is in a position that you know. So if you look at the corners, they all are occupied. All 8 corners are occupied by a green sphere, and the green is the sulfur. So we have 8 times corner, and I'll put sulfur here, and that means we have 1 sulfur from the corners. But there are others here, right? So this, to me, you can see is the face. Okay? So these 3 I can totally tell are on the face, maybe even these 4. Well, if there's 4 on the face, chances are that these here, that I'm going to put an X in, are also on the face, so that we have 6 times the face, which would be, I should have 1/8 here, and I should have 1/2. That has to be somewhere in here. And so that would be 3, right? So the alternative, the other position that this sulfur could be, and it could be completely inside of it, right? If it's not in the face, if it's just a little bit in it, if it's completely embedded, that's a possibility, but chances are that all 6 faces are occupied, in this case, by a sulfur atom. So those are all the green ones, and so we have 4 sulfur ions, and if you wish you can do that, embedded or as part of the unit cell. So now we're going to look at the zincs. So those are maybe harder to visualize, but what I would do is I would focus on the 4 sulfur ions that the zinc is attached to, right? So this sure looks like a tetrahedron, and if you have a corner and a face and a face and another face, there's no other way to put the zinc other than inside of it. So all of those, and this is easier to tell here, but all 4 are inside. So you have 4 times inside, and that's a full, and that's a zinc, and so that's 4 zinc ions. So the unit cell content are 4 zinc ions and 4 sulfide ions. So that's not so hard once you go step by step and slowly go. Same here, right? We have 8 corners, so 8 times calcium corner. That's going to be equal to 1. Then we have the 6 faces again. All right, 6 times calcium. Oh, I should have said 1/8 here. 1/2 face 3. And then all the fluorines are inside, and there's 8 of them. So we have 8 fluorides inside. So there's 8. So we have 4 calcium ions and 8 fluoride ions, which, you know what? CaF2, smallest ratio, makes a heck of a lot of sense, right? So that's the unit cell content here. Here we have a rutile structure, titanium oxide, and so titanium in the corner, we have 8 in the corner, and that's not a cube, but you can definitely have the same argument here. A corner is going to have to share 8 other, so total of 8. So times 1/8, that would be 1 titanium. Then there's 1 on the inside, so there's a titanium times 1 inside. So you want to label this inside. And then that gives me 1 titanium for a total of 2. And now looking at the oxygens, so it's not in the center of the face, but these are clearly on the face. So we have 4 times oxygen on the face, which is a half. So that gives me 2. And then the other ones here, they have to be in the inside here, right? If this is in the corner, this is like if you draw a line or through here, these 2 have to be in the corner, in the inside of it. So 2 times oxygen inside. God, I'm so sloppy. So this is an oxygen, 2 oxygens, and this is another 2 oxygens. So we have Ti times 2 and O times 4. That is the unit cell content for the rutile structure shown here. This is just a bunch of examples of how they crystallize. So rock salt is a face center cubic unit cell, and so it's not just sodium chloride that crystallizes there. I also have lattice energies. Note that they have the lattice energies that are positive. By definition, they should all be negative, right? Okay, some more examples and some more examples, and then finally I'd like to show you what will be on the exam. So this is going to be on the exam. Determine the unit cell content for this semiconductor yttrium, barium, copper oxide. So YbCO semiconductor. This is the unit cell. This whole thing is the unit cell. These lines are just there. And so then you have to kind of go through. I'll give you a couple of hints, like, okay, so there's something on the corner, but this here is not a corner because this is not 3 cubes. This is 1 big box. So I'll leave this up to you. Feel free to email me and ask me, but that's the end of that.